Today's discussion, we're going to look at a really surface view of acid-base reactions. So for acid-base reactions, let's go ahead and start by focusing on the acid. Whenever we have an acid-base reaction, what we have is H plus is transferred from one species to another. We are going to refer to this as a proton from here on out. Because if you have a hydrogen atom, okay, and then it loses its electron, all that's left is a proton. So that's why we call H plus a proton. So here is an example of an acid-base reaction. And in this case, HCl, so hydrochloric acid, is going to be giving up this proton. And this proton is going to go with this water molecule. And we're going to be left with H3O plus and then Cl minus. So notice that hydrochloric acid gave up its H plus, and now all we have left is the chloride anion in the solution. This reaction is essentially 100% for strong acids, like we denoted last time, and then for weak acids, it doesn't occur nearly to that efficiency, but we can still predict the products. So for down here, we have acetic acid, CH3COOH, plus H2O. So what will happen is this acid is going to give up its H plus, so we'll end up with H3O plus as one of our products. And then we'll end up over here with CH3COO minus. So some of the terminology that we'll use is, so this is called our acid, okay? Water in this case is behaving as our base. And then as we start to look at the products, acetic acid was our acid, but now that it's lost its proton, we have what's called the acetate ion. This is now known as our conjugate base. So this is paired with this one right here. And then H3O plus right here. This is what we would call our conjugate acid, and that's related to that base right there, okay, because that base, H2O, accepted a proton. Here's a list of some common strong acids, and what we'll see for acids is that acids tend to have sour taste. For instance, vinegar is an acid. They'll change colors in plant dyes. They'll also react with metals, so a sample reaction for that would be, let's go ahead and consider the strong acid, HCl, so hydrochloric acid. So if we have hydrochloric acid, and then we react that with magnesium metal, what we'll see is we end up with a product of magnesium chloride, and whenever acids interact with metals, we tend to generate hydrogen gas. So this is a sample reaction for an acid reacting with a metal. So now let's go ahead and talk about bases. So the bases that we're going to consider right now are going to be strong bases. And a strong base, for our definition right now, will dissolve in water to yield a hydroxide ion. So recall that hydroxide is OH minus. And strong bases will dissociate nearly completely, just like strong acids will, okay? So recall that diagram that we showed, that the base will essentially dissociate completely to form the cation and the anion. And then for a weak base, these will still produce hydroxide ions. So this would end up forming NH4 plus your hydroxide ion. But this reaction will not occur nearly to the extent of a strong base. So it's still going to produce your hydroxide ion right here, but it's not going to be nearly as efficient or go nearly to the completion rate that a strong base will. All right, so what happens whenever we start to mix these together, and then what's going to be our definition for an acid? So let's go ahead and use the Bronsted-Lowry acid and base definition. So our definition for an acid will be something that donates a proton. So if you recall HCl, hydrochloric acid, we said that HCl dissociated into H plus and Cl minus. So this is what we would call a proton donor. Okay, and then if we go back and look at our example of a base, what we'll see is this is going to be a proton acceptor. So for instance, whenever we had NH3 plus H2O, this would go on to form NH4 plus, so the ammonium ion, plus OH minus. So this ammonia molecule accepted a proton and we formed NH4 plus. So Bronsted bases are proton acceptors. Another thing that you should be aware of, but we won't go into that much detail right now, is monoprotic versus polyprotic acids. So this just means whether you have one proton or more than one proton. So for instance, hydrochloric acid has one proton that it can donate, whereas phosphoric acid has up to 3 protons that it can donate. So that's some basic background for Bronsted-Lowry acids and bases. Let's go ahead and look at an example of an acid and a base reaction, and we'll call this a neutralization reaction. So for this particular reaction, we have an acid plus a base, and it yields a salt and water. So here we have the strong acid, hydrochloric acid, plus the strong base, sodium hydroxide. What we'll see is, so HCl, hydrochloric acid, is going to donate its proton, whereas sodium hydroxide is going to accept that proton. So we end up with H2O, and we also have our salt sodium chloride right here. So this is an example of a neutralization reaction. So we won't get too much into pH right now, but more or less what's happening here is we have something that's acidic and something that's basic, and whenever we mix them in an equimolar amount, so we have the same number of moles of the acid and the base, we end up with a product that essentially has a neutral pH. And we'll go into much more detail later in the semester. But let's go ahead and consider one more neutralization reaction. So let's consider the reaction of hydrofluoric acid, so HF plus potassium hydroxide. Okay, so what are the products going to be? Well, again, hydrofluoric acid would donate a proton, and then this will accept a proton, so we'll end up with H2O plus our salt, which would be potassium fluoride. So this is how you'd go about predicting the products for an acid-base reaction. So next time we'll pick up with oxidation reduction reactions, and then we'll start to classify types of reactions as well.